This video we'll take a look at redox reactions and how to classify them. In a previous video, we took a look at the 6 basic chemical reaction types. An additional reaction type is a redox reaction, which 4 of the basic chemical reaction types can classify as a redox reaction: single replacement, combustion, combination, and decomposition. Redox reactions involve the transfer of electrons within a reaction. As the number of electrons assigned to individual atoms changes. And if we're looking at reactions involving covalent compounds, those electrons are rearranged as bonds are broken and new bonds are formed. And we'll see how we can determine whether we have a redox reaction with covalent compounds. Oxidation reactions involve oxidation or reduction, and we call them redox because oxidation has to occur with reduction. Oxidation is the loss of one or more electrons, or the acronym OIL, O-I-L. Reduction is the gain of one or more electrons, or the acronym R-I-G, RIG, oil rig. So oxidation can also be considered the addition of oxygen atoms to an element, or the removing of hydrogen atoms from a compound. Similarly, reduction can also be the removal of oxygen atoms from a compound, or the addition of hydrogen atoms to an element or compound. If we take a look at this schematic down on the bottom, notice that what happens in a redox reaction, we have a substance that becomes less negative when it's oxidized. A substance is going to become less positive when it's reduced. And notice that electrons are always going to be involved in this reaction. Either we're losing them in the forward or gaining them in the forward reaction. So as I mentioned, redox always occurs together. When one substance loses its electrons, another substance gains those electrons and are reduced. So in essence, one substance causes the reduction of another, and the substance that causes the reduction of another is called the reducing agent. If it is the reducing agent, it becomes oxidized. So I have to give up my electrons to force something else to become reduced, right? So an oxidizing agent is just the opposite. It causes oxidation. So in order to cause oxidation, that means it's going to force a substance to lose its electrons, and then it takes those electrons on itself as it becomes reduced. So reducing agent is oxidized. Oxidizing agent is reduced. So here we're going to take a look at these reactions, same reactions that we looked at in a previous video, and we're going to take a look and figure out if we can determine these reactions as a redox. Well, from the very first slide, we said that a redox reaction can be decomposition, it can be single replacement, it can be double replacement, or a combustion reaction. So remember those to determine what can be a redox reaction. Let's take a look at the first box. We have, in our first box, we have a double replacement reaction for the first one. And because it's double replacement, it is not redox. We have here the second reaction we have is a what kind of reaction? It's a synthesis reaction, and it could possibly be a redox reaction. We'll find out in a moment. The third reaction, it's also a double replacement. No redox available there. Why? Because all of the ions maintain their normal charge. They keep their electrons. They don't lose them or gain them. They keep them. The fourth example, we have zinc plus sulfur to give us zinc sulfide. That is a combination reaction, so it's possible for it to be a redox reaction. We'll see. And the very last one, once again, we have another double replacement, so it cannot be redox. Take a moment and look at these 2 other boxes to see which of these can be classified as a redox reaction, and I will come back and give you the answers. Okay, let's take a look to see if you pick the right reactions. The first reaction in our second box is a decomposition reaction. It can classify as a redox reaction. Our second reaction is a single replacement, which can also classify as redox. The third reaction in the second box is a combustion reaction, so it's probably redox. And the same goes for the very first reaction in the third box. The second and third reactions in the last box are both, as a matter of fact, the second, third, and fifth reactions in our third box are all single replacement. They're all single, not the top one, forgive me. They're all single replacement, and so that means that they're possibly redox. So let's go through and determine what the oxidizing and reducing agent is. Okay. Let's take a look here. Our first reaction we have is a synthesis reaction. It's a combination reaction. And if we take a look at what's happening to the atoms here, notice that our first compound is ammonia, and our second compound is HCl. Notice that ammonia has 3 hydrogens attached to it in the reactant side. However, on the product side, it's got 4 hydrogens attached. If we go back to one of our definitions, if you gain hydrogen atoms, then you become reduced. Oh, so since NH3 is reduced, then it is the oxidizing agent. So that means automatically that HCl is going to be oxidized, and it is the reducing agent. So if you determine one, you automatically know what the other reactant is. Let's take a look at the second one. In this reaction, we're looking at a metal plus a non-metal that are coming together to make one compound. If you remember, metals plus non-metals generally give us ionic compounds. So what we can say here is that zinc has 0 charge when it's a solid by itself, and so does sulfur. But in a compound, zinc becomes a 2+ and sulfur becomes a 2-. So we notice that there has been a transfer of electrons because zinc actually does what? Zinc loses electrons while sulfur gains them. So in a sense, if zinc is losing, then that means that zinc is oxidized, so it must be the reducing agent. And similarly, sulfur is reduced, so it is the oxidizing agent. Take a look at the next problem. We've got aluminum sulfide decomposing to give us aluminum plus sulfur. So what's happening here? In this compound, we've got a metal plus a non-metal. Then that means we have another ionic compound. Aluminum has a +3 charge in this compound, while sulfur has a -2 charge. However, as elements, they have no charge. So aluminum does what? Aluminum ends up with a 0 charge. That means it had to gain electrons. And sulfur now goes from negative to 0, meaning that it loses electrons. So what happens? The aluminum sulfide which we can actually say the aluminum in aluminum sulfide is, it gains electrons, so it is reduced, and it is the oxidizing agent. Whereas so we'll put this aluminum, the aluminum 2, hey, go away. The aluminum 3 plus is what's reduced, and it's the oxidizing agent. Whereas the sulfur 2 minus within the Al2S3 is oxidized, so it is the reducing agent. Let's take a look at the last example. Notice that we didn't take an account of the number of electrons that are being lost and gained. You would have to do that, and you would need to balance the equation, but it's not necessary. We can still see what's going on without balancing the equation. All right, so what's going on here? H2SO4 is actually an acid, and it's essentially this. What we don't have here in this reaction is that this is an aqueous solution, and we pour that onto some iron solid, and we end up with hydrogen gas. It's like you pour sulfuric acid on top of iron, it bubbles and fizzes, and we end up with hydrogen gas, and we end up with iron sulfate, which is a salt. And it's a solid. Okay, so within H2SO4, that hydrogen has a +1 charge. But when we look at hydrogen as an element, remember hydrogen is a diatomic element, so those atoms, they're covalently bonded, but they have no charge to them. Iron as a solid, as an element or an atom, has no charge as well. However, in iron sulfate, because sulfate is a +2 charge and we only have is a -2 charge, then our iron must be a +2 charge. So let's see what happens. Hydrogen gains electrons, whereas our iron loses electrons. So it is the H plus within the H2SO4 that gains those electrons, so it is reduced. So it is the oxidizing agent, and the iron is oxidized, so it is the reducing agent. I will do one of these problems. I'll do one of the combustion reactions, and I'll do one of these synthesis, and I'll do the, let's say, I'll do the single replacement reaction. I'll do one of the combustion and one of the single replacement reactions with you, and then you can practice on your own, pause the video, practice on your own, and I'll come back and give you the answers. So let's take a look at the first combustion reaction. Remember we said that when looking at covalent compounds, you look to see the loss and gain of hydrogen atoms. So let's take a look at this whole compound. Carbon is attached to a bunch of oxygens and hydrogens, right? However, when we look at carbon on our product side, it's only attached to oxygens, right? We've got these hydrogens here that are generally attached to oxygen atoms. And when we look here on the other side, it's also attached to oxygen atoms. But what is different? Notice that carbon loses a bunch of oxygens in order to become CO2. It loses a bunch of hydrogens and oxygens. However, remember what I said in the very first video when we were talking about different types of reactions, combustion reactions involve the oxidation of hydrocarbons. So if it's an oxidation reaction, then that means that O2 is the oxidizing agent. Oxidizing agent. And it causes the reduction. No, pause that. So it is reduced, and our hydrocarbon is oxidized by the oxygen. So it is the reducing agent. So you can memorize the rule for combustion reactions, that oxygen is always going to be the oxidizing agent, and the hydrocarbon is always going to be the reducing agent. Why? Because it becomes oxidized, right? And we are going to do the fourth one here together. All right, let's take a look what happens to everything in our compound. Magnesium has a +2 charge. Our phosphate, we know it's going to be a 3-, but and then our hydrogen has a 0 charge. In our products, magnesium, because it's an element, it has no charge. And in hydrogen, because it's now an acid, remember, as an acid, the hydrogen is going to have a +1 charge. So what has happened from our, and phosphate keeps its same -3 charge. I'll put it there. So what's happened to magnesium and hydrogen? Magnesium goes from a +2 to a 0, so that means that it gained electrons. And hydrogen is going from a 0 to a +1, then that means it loses electrons. So the magnesium ion, 2+, within the magnesium phosphate is reduced, so it is the oxidizing agent. And the hydrogen is oxidized, so it is the reducing agent. Take your time, pause the video, and come back, and we'll give you the answers for the last 3. Okay, remember, all combustion reactions are the same. Oxygen is the oxidizing agent, and the hydrocarbon is the reducing agent as it gets oxidized. Let's take a look at iron plus oxygen to give us iron 3 oxide. Notice that iron goes from a 0 charge to a +2 charge. That means it has lost electrons, it's oxidized, it is the reducing agent. Oxygen goes from a 0 to a -2 charge, meaning that it gains electrons, it's reduced, so that makes it the oxidizing agent. Notice that in a reaction that contains oxygen, oxygen is always the oxidizing agent, and the other compound is the reducing agent, correct, because the oxygen causes the oxidation of the other compound. All right, let's take a look at the very last one, with chlorine plus potassium bromide to give us potassium chloride and bromine. Notice that our chlorine has a 0 charge to start with, and it ends up with a negative charge. It gained electrons and was reduced, so it is the oxidizing agent. The bromine, or the bromide ion within the potassium bromide, has a negative charge. Bromine as a compound or as an element has a zero charge, and so it has become oxidized, and it is the reducing agent.